So in our new chapter, we're talking about finding the centroid of an area. We will move on to find centroids of lines and volumes, but I think the area is a good sort of way to introduce the idea. And basically the centroid is kind of like the center of mass, except we're really just solely basing it on the area. And so it is a weighted average where the position is weighted by the area that's located there, and then of course we divide by the total area. So if you start to think about it, it might look really familiar and very similar to how we would define the center of mass, except that instead of dA, we would have dm. And it really is, and it's exactly the same in the cases where the mass would be distributed evenly along the area. And that's why centroids are useful, because in the cases where the material is distributed in a uniform way, finding the center of the area is equivalent to finding the center of mass or even the center of gravity. Now in the definition, we have, like I said, we have the x position weighted by the area if we're finding the x centroid. If we're finding the y centroid, we have the y times or weighted by the area there. And what I had written here is that you want to choose the dA so that everywhere along that area it has the same value or x or for x or y, depending on whether you're finding the x centroid or the y centroid. So I'm going to work with this relatively simple curve. It's y squared equals x, and we're only going to look at it from 0 to 1. So it stops right here. And I wanted to sort of diagram how we would find the dA for the two situations and sort of help illustrate what I meant by this statement. So in this picture, we're showing how we would set it up to find the x centroid. We want to find the area, use the area so that everywhere along this dA it has the same x value. So you see that in that situation, it's vertical. It has a vertical, it's a vertical strip. While when we do the y centroid, we want the whole area to have the same y value, so it's a horizontal strip. Now, this is going to affect how we integrate and also how we express the dA. Now, in this, when we look at the dA, you know, in general, it's a rectangle. It's the height times the width. And the width is dx, right? Because that's how wide it is. The height is actually y. But so let's put that in here. So I have x, and then I have y dx. And down here I have y dx. Now the problem with this is that you have two different variables in this integral, and the dx indicates that I'm integrating over x. So I need everything to be expressed in terms of x. And so for this particular situation, the height here is the y value, which is actually the square root of x. So it says y squared equals x. So y is the square root of x. And so replacing the y by the square root of x, now I have everything in terms of x, and I have relatively simple integrals to do. The top and the bottom can be done totally separately. In fact, they should be. And you're just having x raised to a power, and you have to integrate it. So you should be able to do that. It's like integrating a polynomial. Now, for the y one, things look a little bit different. And we can still say that dA can be written as the height times the width. But this time the height is dy, and the width is basically the value of x here minus the value of x here. So I'm going to just write it as x, shoot, that's not an x on the right minus x on the left. Okay? Well, what is the value of x on the right-hand side of that strip? That's a vertical line, and everywhere x is equal to 1. So it's 1 minus, and the value, oops, I had an x squared there, it didn't belong there. On the left-hand side, the x on the left is also related to the y, and so I can write it as y squared, because it's bound by the curve, right? So in this scenario, I have y times dx times, oh, what? No, it's dy. What am I thinking? It's dy times 1 minus y squared over the integral of dy times 1 minus y squared. So the dy times 1 minus y squared represents the dA, and y, of course, was the y variable. And this goes, y varies from 0 to 1 in both the top and the bottom. Now, in this particular integral, I'm going to go all the way through because I want to show you another way to get after this. And so I want to have the answer so we can do a comparison of two different methods for finding this centroid. So this integral on the top, I have to distribute before I integrate. Turns into y minus y cubed, and the integral on the bottom is just 1 minus y squared dy. And again, the limits are 0 to 1. When I integrate on the top, I get y squared over 2 minus y to the 4th over 4, and then y minus y cubed over 3. And both of these have to be evaluated at 0 and 1. Okay, now these are really nice because they're evaluated at 0 and 1. And when we square 1 or we take it to the 4th, it's just 1. So on the top, I have 1/2 minus 1/4. On the bottom, I have 1 minus 1/3. So I have 1/4 divided by 2/3, which is equal to 3/8. All right, so this is a really traditional, very straightforward way to write and to find the centroid. Now, I want you to imagine that I have a situation where this is my graph. This is my graph, some sort of circle. This is the x-axis, this is the y. In this scenario, if I used my traditional approach of finding the y centroid for this curve, I would end up getting into a situation where I didn't know how to proceed. The problem is because the same curve is bounding the right-hand side and the left-hand side of my area element. And I don't know how I can differentiate between this coordinate and this coordinate. Even if I had the functional relationship, this would be basically impossible to do. And so in these scenarios where you're having trouble with your normal sort of vertical or horizontal strip, the approach, like for x's, I always take a vertical approach, a vertical strip, so they all have the same x values. And for the y, I always take horizontal strips, so they all have the same y. It's not working here. And so I want to show you another way that we can go about doing this calculation. So I want to just get rid of this so I have a little bit more room. And so another definition that I can use for the x and the y centroids, I'm just going to pop it up here. And you see, you're going to say, well, it almost looks exactly the same, except here you have x with a squiggle on it and y with a squiggle on it. The x with the squiggle and the y with the squiggle represents the centroid of dA. So when you're taking the strips, what you're doing is you're finding the location of the strip, the centroid of that strip, taking that coordinate and weighting it by the area. So let me draw a picture of the curve again and show you what we would be doing to find the y centroid in a different way. So I'm still going to use the same curve because I want to show you that I'm going to get the same answer. So what I'm going to do this time is, instead of use the traditional horizontal strip to find the y centroid, I'm going to take vertical strips, and so they have an area dA, and each one of those strips has its own centroid y squiggle or y tilde, and I'm going to find the location of that y tilde and put that into my integration, like right here. How do I find y tilde? What I'm going to do is so I have here the y at the bottom and the y value at the top. And so I'm going to start with the y bottom value. And basically, I'm going to add half the height, which is going to be the top minus the bottom. Now, you might think that I'm going to do a lot of extra work because the y bottom is just 0, and so it's pretty obvious that the y tilde for this strip is just half of the y value. But it's not always true that we're bound by the x-axis or the y-axis for our bottom value. And so we have to sort of allow ourselves to think about how we would do it more generally. For instance, if I had a curve that maybe looked more like this, and I'm trying to find the centroid of that value, now you can see why knowing the y bottom and the y top is going to be a lot more helpful. If I take this expression and I simplify it, it actually ends up to be y bottom plus y top over 2. You can do the math if you want to check that. And so we're going to use this approach to find the y centroid of this particular curve once again. We've already done it, but we're going to do it again. And basically what we're doing, the reason we're doing it is we want to see that it works, because I already know what the value is. I found it, 3/8. And I want to convince you that I can use this other method and still get the right answer. So y centroid can be written as y tilde times dA over dA. Now, the y bottom plus the y top, the y bottom is 0. The y top is going to be, well, I'm just going to write it as y top over 2, and then times the height of the strip, which is y top, times the width, which is dx. And on the bottom, we got y top times dx. Now, here's the problem we have to tackle. Is we have some of this in terms of y, but our dx tells us we're going to integrate over I'm going to integrate over the x. Sorry, I'm losing track of my thinking here. So what is the value of y at the top? If I take this expression and I solve for y, I take the square root of both sides, I get the square root of x. So I'm going to bring the 1/2 out here. I get the square root of x for y top, here's the half, and then times the square root of x, again, for this term, times dx. And on the bottom, I get the integral of the square root of x dx. And so this ends up to be 1/2 the integral of x dx. It fit barely over the square root of x dx. All right, so that was the integration I have to do. Remember, it goes from 0 to 1. I'm going to squeeze it in here. I get 1/2. The integral of x dx is x squared over 2. And I'm going to evaluate it, that is 0 and 1. And on the bottom, I get actually x to the 3/2 divided by 3/2, evaluated at 0 and 1. Okay. I know it's bad, I squished that in there, but hopefully you can see it. So the top ends up giving me 1/4. The bottom is going to give me 2/3. And so it's 1/4 times 3/2, and I get 3/8. I got the same value, which I should have. I should be able to do it more than one way and still get the same answer. So sometimes you can do the centroids in the very traditional way. Keep in mind there, we're taking the area so that it all has the same y or x value depending on which centroid you want to find. Or you can find a strip and find the centroid of that strip and do the integration using this. And some of the integration tricks are trying to figure out which variable you want to write everything in terms of. Basically, your differential, whether your area has a dx or a dy in it, is what is going to determine your variable of integration. If for this vertical area, because it has a dx width, we want everything in terms of x. Where this horizontal strip had a height of dy, so we wanted everything in terms of y when we integrated. So hopefully you can follow this. Keep in mind you can always stop the video and take a closer look and see these two different ways to find a centroid.